Okay, so we're going to be looking at conservation of mechanical energy and the work energy principle. Two fairly similar things, really. Ultimately, all of this together is just this concept of conservation of energy. So, in the past, we've used things like Suvat equations for situations where you've got constant acceleration, and what we haven't done when we're using Suvat equations is consider these concepts of energy. So now we've defined things like potential energy, kinetic energy, and work done. So with these formally defined, we can start to build up this new framework where we use the tools of considering energy to solve problems, right? So we know certain things about a situation, we can predict what will happen, we can figure out how long something will take, how fast something is going to end up going, and rather than using things like Suvat, which only work for certain cases, we can start considering energy. So one just sort of thought experiment, I suppose. You may already know about this particular example, but it's a good one, I think. You've got, say, someone firing a gun up in the air. I've called it here celebratory gunfire, which is apparently its own thing. So if you fire something at a high speed, for instance, a gun directly up into the air, presumably it goes up, and then what ends up happening is not going to end up going into orbit. It's not that fast, so it will come back down to Earth. If I fire at 100 meters per second upwards, straight up, how fast will the bullet be going when it hits the ground again? And consider also what assumptions are we making, and what how if I vary those assumptions might I get a faster or a slower speed. So have a think about that before I discuss the answer. Okay, so in this case, well, it definitely won't be going faster than 100 meters per second when it lands. I think what we should do is consider a simplified scenario, which is very much simplified. There's no air resistance. Okay, so if you were, say, on the moon doing this, or out in space, but on some solid land, it turns out gravity itself is not an issue. So it doesn't matter how strong the pull of gravity is, and here's the point. It doesn't matter if G is 9.8, it doesn't matter if G is 5 or more, it doesn't matter what planet you're on. If there's no air resistance, I fire in the air, it'll be coming back down at exactly the same speed. And the reason for this is what we're going to be talking about in a moment, conservation of energy. So if I fire the gun upwards, at that point, if I'm on the ground, there's zero potential, but there's a very high kinetic. And then contrast that to what happens when the bullet reaches the peak of its journey. It comes to rest for just a moment in the air, and then it starts falling down again. So at that moment when it's at rest, how much potential energy must it have? It'll have exactly the same amount of potential energy as it had kinetic energy when it started. And then when it comes back down to Earth, the situation reverses again. It's almost a symmetry. That potential energy that it had when it was high up in the air gets fully converted back into kinetic. When it comes back to the ground, it comes down at exactly the same speed. So in a perfect scenario, if you fired directly up without any air resistance and there was nothing else affecting its motion, the bullet will come straight back down and effectively hit you at the exact same speed that you fired it. The assumption then, of course, which is a big one, is that there's no air resistance. The reality is on Earth there is, which means some of that energy will be lost to the environment in some sense, which will mean that not all of that potential becomes kinetic, and therefore it comes down a bit slower, although surprisingly not that much slower. Okay, so that's it. That's the thought experiment there. And this concept of conservation of energy is what we're going to be looking at a little bit more now. Okay, so let's talk about the principle of conservation of energy. I'm sure you're aware of it, especially if you've done physics. This idea that energy can't be created or destroyed. It's just this quantity which is almost passed between objects, and that the universe, in some sense, has the same amount of energy at all times. It's just passing from one form to another. This can then be used to form a sort of narrower concept, which is the conservation of mechanical energy, which I think I'll just specify here. So this concept of conservation of mechanical energy, ultimately it amounts to kinetic energy and potential energy. And what we effectively say is that at all times, if you have an object and you take its kinetic energy and its potential energy, add them together, then this is going to be the same at all times. Okay, so this is for some object. Okay, the constant itself is not particularly relevant, especially because the constant isn't really a meaningful value, because it will depend on how you define your potential energy zero level. So kinetic energy, there's no ambiguity. Zero velocity is ultimately quite clear in most situations. It's just at rest. Whereas a potential energy of zero is just wherever you happen to have set your zero line. So if you set your zero line to the ground, that's potential energy zero. If you set your zero line at sea level, or at the top of a mountain or the top of a wall, that's your zero level. So the constant itself is kind of meaningless. But what this means is that you effectively have this scenario, right? The kinetic energy, the initial, let's say, if you're comparing two different points in time, then the initial will be equal to the final, right? All that second line is really doing is just taking the first line, k plus p is constant, taking it for two different timestamps, the past and the present, or the present and the future, two different timestamps, and equating them, and we call them initial final. So that's one way of expressing it, to say it's constant. Or another way that might be useful is, rather than talking about the specific kinetic energy, we just use delta to talk about change. So an alternate version of writing this expression would be to say the delta of kinetic energy, which is the change, plus the delta of potential energy equals, and now what does it equal in this case? So just a reminder, the delta of kinetic energy, that is kinetic energy final minus kinetic energy initial. This is the definition of the delta in this context. The potential energy final minus the potential energy initial. So if you just consider, what is this thing here in the green? Ultimately, it's the same as this, right? Except everything has been moved to one side, effectively. So the right-hand side must be zero, right? And that's I suppose, a more natural way of referring to, of using the equation, is to say the difference of one plus the difference of the other, or the change, I should say, add that together is zero. The total change is nothing. So then you don't have this sort of weird, it's not that weird, but you don't have that constant, this sort of slightly meaningless constant, really. You could think of that constant as being the total, energy in the system, but that sort of excludes other forms of energy, and as I said, the potential energy is a bit arbitrary in some sense. So you might prefer this version, okay? But be happy to be comfortable with both. The intuition is fairly clear, I think. It's just that the total doesn't change, so you can interpret it in either one of these forms when you answer these questions. So there's one very important thing about this, one caveat, I suppose. This works, all of this if we're talking about a closed system. And what do I mean by a closed system? This means there's no external forces. In fact, I think I won't use the word enclosed system here, because it does have to be a closed system, but in addition to that, we need no external forces. So it's actually stricter. I wouldn't quite say that's the definition of a closed system. Instead, this is the key thing. There's no external forces. One exception to that, gravity, because that's how potential energy is defined. Okay. So you can use these equations whenever there's no external forces other than gravity. So these are situations such as I shoot a bullet into the air, I throw a ball, I create a projectile, anything that's in free fall and there's no air resistance, or I shouldn't say free fall necessarily then, something that's falling down and there's no air resistance. These are all cases in which you've got this very simple kinetic energy plus potential energy. If you've got someone, you sometimes have questions where you'll have skiers on a hill, sort of winding themselves up and down through the landscape, and if you've got no driving force from the skier and no resistance or friction, then you can use this as well. If the only thing that's changing is the height and the speed, but no other forces, then we can use this. Okay, so now, next slide, we're just going to generalize this a bit, because it might seem a little bit useless, or not useless, but it's a bit irritating that we can only do this for situations with no external forces. It would be useful if we had an alternate version of this equation where you can consider external forces, and that's what we're going to look at on the next page. Okay, so now let's talk about the work energy principle. I think some of this naming is a little bit, not necessarily confusing, but it really, both these things we're talking about, this slide and the one before, ultimately they're the same thing. It's all about conservation of energy. The work energy principle is simply the conservation of mechanical energy, but with external forces allowed. So explicitly, so this considers external forces other than gravity. And the way these are included in the equation is by considering what is the work done by these forces. So the easiest way to present this one, I think, is as follows. Consider the change in kinetic energy and the change in potential energy. And if there's no other forces than gravity, we said that was 0, right? Reflect for a moment on the fact that clearly, in this version of the equation, one of these deltas must be a positive number, one must be a negative. If your kinetic increased, then your potential decreased, and vice versa. So what if, for instance, let's say I increased in kinetic energy and I increased in potential energy? How could that possibly happen? Well, that could only happen if there was some external force, like a driving force, increasing the total energy of the object. So for instance, let's say you've got, I don't know, let's say you've got a ball that's sort of been rolling along and then it starts rolling up a hill. As it rolls up that hill, its potential energy will increase, and its kinetic will decrease. So it'll be going higher, but it'll start to slow down. If that ball going up the hill is sort of given a kick as it goes up the hill, suddenly it'll have an increased speed and it'll continue increasing in potential energy. So the total energy has increased. They're both positive now, from initial to final. The change is positive. So what's happened is this force has come along, this kick, and a force acted over some distance, depends how, how much contact I had with the ball as I kicked it, but ultimately some work was done, right? Remember, work done is energy. So that works perfectly in this equation, right? Because this is all about comparing quantities of energy. So what we can say is it will be the work done, right, in some sense. But I think the best way to write this is to say is two kinds of work. The work in, which is work that has been done that contributes energy to the system, and minus work out, and you'll see this a lot on Matter style questions. They'll have this in the writing in the mark scheme. Work out is stuff that has taken energy out of the system, like friction or air resistance, things that take the energy of the object and they sort of take it out into the environment, right? So let's just make a note on both of these, sort of some examples. Work in is things like a driving force or a motor. Let's see, pulling something by a string. Let's say pulling tension. And work out will be things like friction, resistance, like air, and so on. Okay, and that's it really. It's all about what makes something a work in or a work out is all about, does the force oppose the direction of motion, or does the force sort of align with the direction of motion, or at the very least some component of it. Okay, friction always opposes the motion completely, so it's very much a work out. And whereas a driving force, like a motor in a car, will be pushing the car along in the direction of its motion, that's work in. Anything that's at an angle to the direction of motion will be one or the other, depending on what the component that is in the direction of motion is. Okay, so this is the work energy principle. It's just a generalization of what we saw on the previous slide. If there are no other forces besides gravity, then work in and work out are going to be zero anyway. Okay, and I think this is probably the most succinct way of writing this. You may want to note that this is final minus initial, and that this is final minus initial, but that's up to you. It should be quite clear. So in this case, both of these can now be positive. They can both be negative, or one is negative, one is positive, vice versa. All four combinations are now possible. Okay, so let's make use of this in some examples. Okay, so we've got smooth plane, 30 degrees. It's smooth, so I'm not going to make it look rough. There's a particle, and its mass is 0.5 kilograms. It's more like 0.5 g. Before I read the rest of the question, actually, I'm just going to very quickly add the components, because you almost always need to do that. This will be 0.5 g cos 30. This is 0.5 g sine 30. And it's always nice to get rid of these coses and sines as quickly as possible, because they're a bit annoying to deal with. So sine 30 is a half, so this is 1/4 g. Cos 30 is root 3 over 2 times a half, so this should be root 3 over 4 g. Okay, slides down the line of greatest slope. It starts from rest at A. Okay, so this is A, and its speed u is 0, and it passes point B with a speed 6 meters per second. So at B, its final speed, let's call it v, will be 6 meters per second. I could use magnitude u, magnitude v, but I'm just going to be a bit lazy now and just use 0 and 6. Find the distance AB. Okay, find the distance AB. So the way we're going to do this is with energy consideration, and then you just want to remember that kinetic energy doesn't care about distance, but potential does. Let's consider then, let's do it this way, change in potential energy. Okay, the change in potential energy, it depends where you have your zero line, what the actual potential energy is, but the change will always be the same. It doesn't particularly matter. Let's just say the zero line is here, right? So that's our 0 PE. So then it goes to B and it'll have lost some potential energy because it's gone downwards. Now, how high is that? Let's say the distance AB, which we want to find is let's call it x. This is our unknown. So therefore, the height h, so this height here, the vertical height, is going to be x cos 30, right? Have I done that right? X, no, x sine 30 would be, sorry, that's vertical. X sine 30, that's nice. So then we get half x. Okay. So what that then tells us is the potential energy lost is going to be minus, or the change is minus mg times a half x, which in this case, if the mass is a half, that's minus a quarter gx. And then consider the change in kinetic energy. So it started with 0, and now it's at 6 meters per second. So kinetic energy is quite an easy one. It's just a half times the mass, which is a half, times the velocity squared, which is 6 squared. And that's the increase. It's a positive number. That's 9, isn't it? Okay. And then we can say, right, well, these two added together must be equal to 0. So therefore, 9 minus a quarter gx equals 0. And that implies that x must be equal to 9 times 4 divided by g. So that's 36 over g. It's always nice to have it in a nice simple form. And then on the calculator, that should give you 3.673, and so on, with g as 9.8. Cool. So that's it. You could, if you wanted to, not use the delta version, and you could instead say something like kinetic energy final minus initial equals this, potential energy final minus initial equals this. It's up to you. Use the notation you're comfortable with, but personally I quite like this one. It's quite quick. Okay, so now let's look at this one. Particle and mass 2 kilograms. It's going up a slope. And notice already, so this is talking about coefficient of friction. So now there are additional forces. So we're going to have to use the more general work energy principle, right? We're going to have to include work in this and not just equate it to 0. So let's do the drawing or the diagram. Very important to have the diagram. It's going up the line of greatest slope. Okay. So we've got a mass, 2 kilograms. Let's see, it's going at a speed initially of 8. It's going that way. That's not a force arrow, that's just me saying it's going up. Inclined at 45 degrees. That's useful, that's good, right? Because remember, sine 45 equals cos 45 equals 1 over root 2, or root 2 over 2, depending on your preference. And then the coefficient of friction is 0.4, so mu equals 0.4. Calculate the distance the particle travels up the plane before coming to instantaneous rest. Okay, so it's a bit similar to the last one, except instead of starting at rest, we're now ending at rest. And that's quite a useful thing to know. How far is it going to go up the plane? V is 0. And we effectively, let's call this A and call this B again, and then we can say the distance AB equals X, and what is it? Okay. So first things first, I think we should resolve those forces on the, or add forces as well. So let's resolve the forces on the weight, split it into two components. We've got 45 degrees, and therefore these should be the same. So that's 2g times 1 over root 2. 2g over root 2 is just root 2g, so we've got root 2g here, and we've got root 2g there. Okay, and then what other forces have we got going on this thing? Well, we've got the reaction force, and we've also got this friction, which is opposing the motion, which I usually call Fr rather than F, and that's equal to mu, which is 0.4 R. Okay, so then considering the forces that are perpendicular to the plane, we've got R going up, and we've got root 2g going down, and nothing else. So therefore, R must be root 2g, which then allows us to conclude that the friction is 0.4 times root 2g. So let's write that, 0.4 root 2g. And then let's think for a moment. I should just point out, in terms of the arrowheads here, I labelled them poorly there, so incorrectly. This force is effectively going that way, downwards, and then this one's going to the left. I think that makes it a bit clearer. Effectively, those two components just replace this one, so maybe I'll just do that. Let's get rid of that, makes it clearer. Those two components can stand in for that single one going down. So now, which forces are actually parallel to the plane? It's just the friction and this root 2g. Now, remember, when we talk about work done, we don't have to worry about the gravity forces, because that is included within the potential energy. So gravity is almost a force that's so important that we just give it its own special kind of work done, which is this potential energy change. Technically, the change in potential energy is work done against gravity, but we don't mark that as the work done in this case. So we're only going to focus on that frictional force as the work done. Right, so let's do some more calculation. What is the change in kinetic energy going to be? So it started as 8, it ended up as 0 in terms of its speed, so it's decreased, so it's lost, in this case minus a half times its mass, which is 2, times its speed that it started with, which was 8 squared, so we get minus 64. And then the change in potential energy, what's this one? It's increased. How high has it gone? So it's similar to before. X is our horizontal along here, our distance on the slope. So it's going to be sine 45 times x, so it's x over root 2. That's nice and easy. And that's then going to feed into here as being the mass of a half times g times x over root 2. So we could write that as x times root 2 over 4 times g. But hang on, this half, that should be a 2. That's the mass is 2. Misread that. Hang on, so that's 2, in which case I multiplied by 4 ultimately, so maybe it's this instead. Let's check. So P is mass 2 times G times H is x over root 2. 2 over root 2 is root 2. Yeah, that should be fine now. Root 2 xg and minus 64. Okay, so let's write it down here. Change in kinetic energy plus change in potential energy equals work in minus work out. In this case, let's write them the other way around here, so we don't have sort of floating negatives. We've got root 2 xg minus 64 equals, now what's the work in? There isn't any, because that friction is not working in our favor. It's working against this object, direction of motion specifically. But the friction conveniently is entirely opposed to the direction of motion. It's parallel in that sense. So we can just use the work done, which is friction times the distance which it acted for, which in this case is x. So friction times x will be our work out. So that's going to be minus 0.4 root 2 g times x. So now it should just be a case of doing some rearranging. Let's use the space over here, and you can always finish it off if you're faster. So we've got root 2g plus 0.4 root 2g lots of x, and that's equal to 64. That implies, well, we've got root 2g and 0.4 root 2g, so that's 1.4 root 2g times x equals 64. So x should be 64 divided by 1.4 root 2 times g. And indeed, we get the right answer. It's equal to 3.298, and so on. And that's the distance. Cool. All right. Just a word on the fact that here, throughout this, I've kind of just stuck with surds. I immediately changed sine and cos of 45 to their surd forms, which was root 2 over 2. I do recommend doing it. I think it makes your working a bit easier, and it also means you're not having to write down, long decimals. Within the textbook example, they tend to just write sine 45, cos 45 over and over again. But what that then means is their final answer looks a bit ugly. Instead of having this nice 64 over 1.4 root 2g, there's this big fraction with a whole bunch of sines and coses in it. So I recommend make use of your knowledge of angles and their standard trig values. Cool. All right. I think that's it for examples. Let's take a look. Yeah. So 2 slides of questions. It's these 3, and then there's one more on the next slide. Just see how you do. Try and focus on using as much of the correct notation as possible. And I would also say practice. Let's go question by question. For 6, no diagram needed, but use good notation. For 5, you want to have drawn a diagram. Don't just try and visualize it in your head. Draw an accurate, nice big diagram, use the notation properly, and see if you can get to the answer without using a calculator partway through. Just it depends on the angle, actually. Does it give us the angle? Oh, it's a rough horizontal floor. Sorry, I take it back then. You might want a diagram for that. Possibly, there's a lot of forces going on. But yeah, you shouldn't need a calculator until the very, very end, possibly. Likewise for 10. Good diagram. Just whenever you've got multiple forces being shown, just have a diagram. Okay, and then let's look at, I'll give you a moment to pause. Pause and have a go first. Okay, and then let's look at the next slide. Okay, so now you've got your slope. I think we'll do a few more with friction involved in the part 2. So we're just mainly working with the principle of mechanical conservation of energy for now. Let's see how you do on this one. You can pause the video now.